In this video we're going to learn how to multiply certain matrices together. We're going to build up that definition step by step from the simplest to the general case. So here is that most simple case, which is that of a row times a column. So let's say we have a row vector r of width n and a column vector c of height n, and it really is important that the width of the row vector is equal to the height of the column vector. We'll notate the entries of our row vector as r1 across to rn, and the entries of the column vector as c1 down to cn. In that case, we define the product r times c to be the number that you get by multiplying r1 times c1 and then r2 times c2 and so on, and then adding up the results. So in sigma notation, that will be the sum from I equals 1 to n of ri times ci. Here's an example. We take the width 3 row vector 1, 2, 3 and the height 3 column vector 4, 5, 6. The width of the first vector is the same as the height of the second, so we're allowed to multiply them, and the result will be 1 times 4 plus 2 times 5 plus 3 times 6, which is 32. The next step in our definition is to do a matrix times a column. So we define the product of an m by n matrix and a height n column vector. And again, it's really important for our definition that the number of columns in the matrix should be equal to the number of rows in the column vector. So the height of the column vector must be the same as the number of columns in the matrix. So I really do mean the same n here as I have here. Okay, so here's the definition. We take an m by n matrix. That means it's got m rows, so we'll call those r1 up to rm, and if we use the definition little a subscript ij to refer to the ij entry of a, then ri will be the row vector whose entries were a, i1 across to a, in. If we then let c be our column vector of height n, then we define the matrix product a times c to be the height m column vector, which you get by doing r1 times c in the first place, r2 times c in the next place, down to rm times c in position m. As an example, let's take A to be this 2 by 2 matrix here. In that case, R1 would be the first row of A, which is 1, 2, and R2 would be the second row of A, which is 3, 4. Let's now let C be the height 2 column vector 5, 6. Now the number of rows in C is the same as the number of columns in A, which is 2, so we're allowed to multiply A by C. If we do that, then by definition, A times C is the height 2 column vector whose entries are R1 times C and then R2 times C. If we do R1 times C, we get 1 times 5 plus 2 times 6, which is 17. And if we do R2 times C, we get 3 times 5 plus 4 times 6, which is 39. So that's our matrix product, A times C. It's the height 2 column vector, 17, 39. Let's do another example where it's a little more complex. So we'll take this time A to be the 3 by 2 matrix whose rows are 1, 2, 3, 4, 5 and 6. And we will take C to be the height 2 column vector whose entries are 7 and 8. So again, the number of columns in A is 2. It's got 2 columns. Let's say column 1 and column 2, and that equals the number of rows in C. C's got 2 rows, row 1 and row 2. So we are allowed to multiply A by C according to our definition. The number of columns in A is equal to the number of rows in C, so we're allowed to multiply them. So when we do that, we do it by forming the height 3 column vector whose first entry is the first row of A times C, and whose second entry is the second row of A times C, and whose third entry is the third row of A times C. So the result is a height 3 column vector. And that column vector would be, well, if we multiply the first row of A times C, we get 1 times 7 plus 2 times 8. If we multiply the second row of A times C to get the second entry of the product, that's 3 times 7 plus 4 times 8. And the third entry of A times C will be the third row of A times C, which is 5 times 7 plus 6 times 8. So we get this matrix here, this height 3 column vector. Okay, finally we're ready for the most general definition of matrix multiplication. This time we take a matrix A, which is m by n, and B, which is n by p. And again, I really do require n to be equal to n, so I really require that the number of columns in A is the same as the number of rows in B. The way we define this matrix product A times B is as follows. We introduce some notation for the columns of B. So we call those C1 up to CP, right? There are P columns of B because B is an n by P matrix, and each one of those is a height n column vector. Then we define A times B to be the m by P matrix, whose columns are A times C1, A times C2, over to A times CP. And those products, A times C1, A times C2, and so on, are the products we introduced on the previous slide. And they make sense because A is m by n, and each of these columns, C1 up to CP, is an n by 1 column vector. So the number of columns in A matches the number of rows in those column vectors, and therefore we can multiply them in the way that we introduced on the last slide. So before I go on and do an example, let's just think of a way to remember the way that these matrix multiplication sizes work. So what we're allowed to multiply is an m by n matrix and an n by p matrix. And the way the sizes work is you should think of the n's in the middle as kind of cancelling out. So the result would be m by p. And that is indeed what happened in our definition. We multiplied an m by n matrix and an n by p matrix, and we ended up with an m by p matrix, so the n disappeared and we were just left with m by p. Okay, so our definition was that AB was the m by p matrix whose columns were AC1 up to ACP, where the C's were the columns of B. So you could draw this in a particular way. A times the matrix whose columns are C1 up to CP is the matrix whose first column is AC1 and whose next column is AC2, all the way across to the final column being ACP. So let's see this in an example. Here A is the matrix 1, 2. So what size is that? That is a 1 by 2 matrix. And B is this matrix here. This is a 2 by 3 matrix, 2 rows and 3 columns. You can see that the number of columns of A matches the number of rows of B. So the answer, AB, will be 1 times 3. It'll be a 1 times 3 matrix. So you should think of the 2's as kind of cancelling each other out here. Okay, let's just make this a bit clearer. A times B will be a 1 times 3 matrix. So which 1 times 3 matrix is it? Well, let's work it out. A times B, according to our definition, is the matrix that you get by doing A times the first column of B, and then A times the second column of B, and then A times the third column of B. So just to make this clear, this column vector here is what I'm calling C1, and this column vector here is what I'm calling C2. That's not very visible, is it? Let's try again. C times 2, C2, and the last column vector here is C3. So that matrix product AB is A times C1, A times C2, A times C3, and if you work those out according to our matrix times vector definition, what you get is 1 times 1 plus 1 times 2 in the first position, then 1 times 0 plus 0 times 1, 1 times 0 plus 2 times 1 in the second position, and 1 times 1 plus 2 times 0 in the third position. Okay, so that is our most general matrix times matrix definition. Let's do another example because this definition is complicated. So this time we will have a 2 by 2 matrix A and a 2 by 2 matrix B. So their product AB is defined because the number of columns of A equals the number of rows of B. They're both 2. So the kind of 2 in the middle will cancel out and the result will be 2 times 2. And the way we form this matrix product is we multiply A into the columns of B 1 by 1. So the way people express that property of matrix multiplication is they say matrix multiplication happens column-wise, or one column at a time, because you get AB by doing A times the first column and then A times the second column of B. So in our notation before, this would be C1 of B, and this would be C2. And the columns of AB will be formed by working out A times C2, that would be the second column of AB, and A times C1, that will be the first column of AB. So to work out A times 5, 7, we do 1 times 5 plus 2 times 7 at the top, and then 3 times 5 plus 4 times 7 at the bottom. You can see that's what I've put in this matrix product. And to work out the second column of AB, that will be A times C2, which we work out by doing the first row of A times C2. That's 1 times 6 plus 2 times 8. That's at the top. So in the top position right here. And this final part of our matrix will be obtained by doing the second row of A times C2, which is 3 times 8 plus 3 times 6 plus 4 times 8, which is what we've got here. Okay, so if you work those out, then you get the actual entries of AB. All right, finally, there is a different way to describe matrix multiplication. This is exactly the same definition, just written in a different way. And this different way is useful for us, not so much for when we're doing actual calculations by hand, but rather when we're trying to prove properties of matrix multiplication. So here is that alternative description of matrix multiplication. If you've got a matrix A, which is m by n, and whose ij entry is A subscript ij, and if you've got a matrix B, which is n by p, and its ij entry is B subscript ij, then A times B is the m by p matrix whose ij entry is this. So it is the sum from k equals 1 to n of aik times bkj. So again, this is precisely the same definition as we've just seen, just written in a slightly different way. And this is a warning. People tend to get a bit confused by this definition, and they'll write things like, they'll say things like AB equals the sum from AIK times BKJ. But that's nonsense, isn't it? I mean, this is total rubbish, because those two things are not even of the same type. A times B is a matrix, this sum is a number. So don't write things like this, because they don't even make sense on the most basic possible level. The two different things there are different. One is a matrix, one is a number. A matrix isn't the same thing as a number. So what you need to do, well, I mean, another alternative way to write this would be to say AB is the matrix whose ij entry is Cij, where Cij is equal to the sum from k equals 1 up to n of aik bkj. That's a way in which people sometimes express the definition I've just made, but don't do this. It doesn't make sense at all. Okay, that's it for our definition of matrix multiplication. In the next video, we're going to explore some of the properties of matrix multiplication.